Good afternoon, everyone in Taiwan and also in Japan. And today is my great pleasure to have Professor Masahiro Suzuki from Nagoya Institution of Technique University. Okay, and today he will share us his recent result already published in archive about the solitary wave of the Vlasov Poisson system. And I think this result, I have already heard of it, and the analysis is very delicate, and the results are very amazing, and today we are very curious about it. So let's welcome Professor Masahiro Suzuki.
Thank you for very nice introductions. And I would like to thank your kind invitation, Professor Dai. And yeah, it is my pleasure and honor to give a presentation in this NCTS webinars. Yeah, thank you so much. So today I would like to talk about a very fundamental question of the existence and the uniqueness of the solitary waves of the Vlasov-Poisson system. So I just consider a very simple question. And this result is obtained through joint work with Professor Masahiro Takayama at Keio University and Professor Catherine Chien-Chan at Northeastern University in Boston, not in China. So, so let me start my talk from introducing Vlasov-Poisson equation. So this is a very usual Vlasov-Poisson equation, but I want to start from introduce notations. So T means time variable and X means space variable. And we just consider on the line, X is just one-dimensional. So we consider line soliton. And velocity, sorry, Xi is velocity, and Xi1 direction is the velocity corresponding to this space X, one dimension, and X prime is tangential velocity for the this direction. And you know that in the Vlasov-Poisson system, these five quantities are independent variable. And F plus means ions velocity distributions, and F minus is electron velocity distribution. And the minus phi is electrostatic potential. And these three functions, unknown functions, which we are looking for. And Q plus minus and E plus minus are positive constant. I omit the meaning of the physical, I omit the to explain the physical meaning of this constant. And yes, this the first line is just transport equation as usual, but I write two equations together. So I mean, here we use F plus minus. So yes, please choose plus or minus to get the one equation. If we consider F plus, this is an equation for ions velocity distribution. And if we take a minus, F minus, that is an equation of electron velocity distribution. And this term comes from the Coulomb's force. So it's given by the derivative of electric static potential. And I mean that this is an electric field. And the potential phi is determined by this Poisson equation. And yes, this is our system. And I emphasize that the independent variable of phi is t and x, not xi. So this is a little bit, yes, different from hydrodynamic equations. And we want to consider solitary wave. So we need to put some end state at the x goes at the x is equal to infinity or minus infinity. So we denote end state by capital F infinity plus minus. And this end state, of course, these it should be non-negative since it is a distribution function. And we put the differential point of the electrostatic potential at the far field. I mean that, yes. I explained this one. So we consider that our solution of phi converges to 0 at the x tends to infinity. So this condition is necessary to solve this Poisson equation uniquely. So usually we have a freedom of the constant for phi to tilt that freedom of the constant. We have to put some differential point. That is a requirement. That is the reason why we require this condition. So this is a program which we want to study today. Before going to the mathematical study, I would like to introduce a little bit physical background of solitary waves. Yes, the experiment of the solitary waves already done a long time ago, 50 years ago. Professor Ikeji and Taylor Volker did this kind of physical experiment. So, horizontal direction, this direction is time, and the vertical direction is density of electrons. Then in this direction, time goes by, and this is the initial time. So then if time passed, there is a two peak like this, and both peak move to this direction. So I mean that this part is one solitary wave, and we can find another solitary wave in here. So it's so difficult to see from this picture. So I want to explain by using this illustration. So this direction is time, and this direction is density. Then initially we have this peak, and this peak move to, yes, two peak move to the same direction. This is of course solitary wave. So this is a physical experiment result. And of course, theoretical studies are also done by using Vlasov Poisson system. So the first things I want to mention that Bohm and Gross pointed out that the difficulty of the analysis lies on the trapped ions. Let me explain what is a trapped ions. If we consider solitary wave, like this, in the case, electrostatic potential also have this kind of shape. This is a traveling wave, I mean solitary wave. And you see that in this area have some potential barrier. So let me explain what is a potential barrier. So we put a positive ion in the middle of the potential. Then from this side, we can get the electric field, and this electric field is push positive ion in this direction. If we look at another direction, electric field push this positive ion into this direction. So this is a trapped, potential barrier. So if the positive ion do not have enough kinetic energy, this ion cannot go out from this potential barrier. So Bohm pointed out that the difficulty of the analysis lies this kind of trapped ions. After that, sorry, I could not pronounce it, these three people. these three people consider a kind of the special waves. Nowadays, people call BGK wave. So let me explain what is a BGK wave. So F plus minus is written by this special form. I mean that, so this small f plus minus corresponding to the end state, which I give the previous slide. And they assume that the solution is written by this form. The phi is an electrostatic potential. So they assume that the solution is written by this form. And of course, we can find such a kind of solution. So this is a main assumption of BGK wave. And these three physicists find the BGK wave in the region that trapped ions are negligible. So this is a first result to find the solitary wave. Of course, after that, many people analyze solitary wave with trapped ions. Indeed, yes. So there is a lot of result, theoretical result of the Vlasov-Poisson equation in the physics. Of course, mathematicians also study about solitary wave, in particular BGK wave. So of course, I mean, mathematicians give analysis with rigorous proof. The first result is done by Professor Guo and Professor Strauss. They showed the existence of the BGK wave, and they also study about the instability of the BGK wave. And very recently, Professor Guo and Professor Lin considered the stability of the BGK wave. So it sounds that there is some contradiction between these two results, but there is no contradiction. So they showed instability for some end state. And this guy studied about stability for other end state. So end state is different. So the stability and the instability really depending on the end state. Anyway, all these results just study about the BGK wave. So we want to study solitary wave beyond the BGK wave. That is a motivation of our research.
So Masahiro, can I ask a question? So
yes.
When you say stability, is always nonlinear stability or linear or something like that?
For this result, nonlinear stability.
Okay, I see.
Yes.
Okay. And what makes the BGK wave unstable? Like, what is the instability mechanism?
Oh.
Oh, sorry. Sorry.
Yeah. That is comes from sorry. I forget the name. Sorry.
No problem. We can decide.
Of course, the main fact is to find to consider the linearized equation. And they found some growing mode.
Yes.
That is a very usual way. So that is their way to find instability. The important thing is to find the growing mode. It's really depending on the shape of the end state.
Yes.
Yeah.
Thank you.
Yes. So I would like to formulate our mathematical program for solitary wave. So of course, solitary wave is a traveling wave. So we want to find the solution which is written by this form and this form. So small f plus minus can be written by capital F plus minus in this form. This is a very standard way to study about solitary wave. Maybe you know very well. So we just consider the traveling wave only x direction. So xi is we do not change anything. And alpha is some positive, some number, and this means the speed of the solitary wave. Alpha means speed of the solitary wave. And we just consider the situation that phi has a unique global maximum point. I mean, our solitary wave of phi given by this form, this way. Of course, we also can consider this kind of shape of phi, but the treatment is completely same. So we just focus on the case that yes, phi has a unique global maximum point. And this is also very usual. We use the coordinate x. This is a coordinate, the same coordinate as a traveling wave. So we use this capital X. Then our program is to find this capital F plus minus and capital phi. Then we easily check that F plus minus phi satisfies these equations and end state. The difference between the previous equation is only this term. Other part is completely same as the previous equation. Of course, this term comes from t derivatives. So we just rewrite t derivatives by this x derivatives by using this form. So the end state is completely same as before.
So Masahiro, can I ask you a question?
Yes, please.
So now your space is one dimensional, but the velocity,
one dimension.
But the velocity is three dimensional.
Three dimensional. Yeah, you're right.
Okay. I'm confused. So it's a particle moving along a line, or
particles can move other direction. So of course, I will go back to our equation. So maybe I just just write some equation. So this is an original equation. Maybe you want to ask this things. This is x. This is x.
Yeah.
So we assume that our functions only depending on x, not a tangential direction. Then we can get that equation. That is the main assumption. So we assume that our solution just depending on x, not the tangential direction x prime. Then this part can be written, P1, x1, f plus minus, and this part is of course.
I see. Thank you.
Yeah.
I see.
So just that is our assumption.
Okay. Thank you. Clear. Thank you.
Yeah. Particle moves any direction. So let me summarize our questions. The first question is, when can we solve the program SW? SW means this program. SW means solitary wave. So this is a very fundamental question. And the second question is, when is the solution of SW unique? So here is a remark. So SW is a system coupled hyperbolic equation and ODE. So still this equation is ODE since we have x derivatives and C1 derivatives. So this is a kind of the difficulty to study about this program. And the second equation is just ODE. So usually if we consider for example, Schrödinger equation or fluid equation, and we consider traveling wave, then traveling waves satisfy just ODE. But our program is still, we need to consider hyperbolic equation, the PDE. This is a difficulty. And for the second question, of course, if we find one solitary wave, and if we consider the translation, we can get infinite many solutions. So, so we want to exclude such a kind of variance caused by translation. Then after that, we want to discuss uniqueness. So these are two main questions in this talk. So, so before showing our main result, I would like to briefly explain what point is difficult for the first question. I mean, more precisely, why trapped ions makes our problem is difficult. So let us suppose that we have a solution, the case that alpha is equal to 0, and the phi has a maximum point at the origin, global maximum point at the origin. Then if we draw the characteristics curves of this transport equation, that picture is this one. So horizontal direction is space x, and the vertical direction is velocity c1. And this curve is characteristics curves of this hyperbolic equation. And the roughly say that the region is divided into these two bold lines. The behavior of the characteristics line completely, totally different in this region. I mean that. So if we consider the upper area, the characteristics line comes from minus infinity, and it connected to the x is equal to infinity. So we can define the variable of f plus by using only end state. So this region is very clear, so no difficulty. But if the lower area is very same, and if we look at the middle area, the situation is totally different. Characteristics curves are closed, are loops. So we cannot define this variable by using the end state. More precisely, we can put any number, any value in this middle area. So in other words, we have a lot of freedom of the trapped ions. So it's so we have a lot of freedom for the variable of f plus on this curve. So this is a main difficulty. And we also have another freedom of potential barrier. I mean that the amplitude of this height is just order of square root of maximum of potential phi. Sorry, square root of phi of, yes. So later on, I will talk about more detail, but another freedom is amplitude of this height. It's really depends. If we consider the very strict potential, this height is getting bigger, wider. So we have another freedom of this height. So these are two difficulty. I mean, in the analysis, we have a difficulty from this freedom. But the one good thing is that all characteristics past this blue line. So this is one advantage. So in this situation, if we know f plus on this blue line, we can determine every f by using this quantity. So this is one advantage. So eventually, we have a freedom of this quantity and this quantity. These two quantities are very the key point to analyze our problem. Anyway, yes, this is a difficulty, and I want to mention our main result. So first of all, I would like to give a definition of our solution. So our solution, yes, f plus minus phi is a solution of SW if it satisfies the following. The first condition is just regularity. This is a regularity. And f plus minus belongs to Rubeg space. So it is a weak solution. And the x direction, is this direction corresponding to x and this direction corresponding to the c. For each fixed x, the function f plus minus belongs to L1 Rubeg space, and it is continuous in x direction. So we consider this kind of the regularity, and phi is a C2, classical regularity. So later on, I will explain why we consider the classical solution only for phi. And the second condition is the qualitative condition. So of course, f is a distribution. It should be non-negative. And as I said that we consider, it has a unique global maximum point like this. So this shape gives by this condition, and we now restricted that our maximum point located at the origin. So using, this condition killed the variant caused by the translation. So the point of the traveling wave is fixed owing to this condition. So the third condition is this is a weak form of transport equation. It's very, standard weak form. I just moved to the derivatives, all derivatives to the test function psi. It is very standard. And our f plus minus satisfies end state in this sense. So when we extend to infinity, it converts to the end state in L1 topology. This one is really corresponding to this regularity. Yes, our function is continuous in L1 space. So this condition really matches to this regularity. And the fourth condition is phi solve Poisson equation in the classical sense. So here is a remark. So we can replace this classical sense by weak sense. Indeed, we see that weak solution is a classical solution owing to this regularity. So this is our Poisson equation. So it has this regularity. So from this regularity, we see that, the right-hand side is a C0 function, continuous function. So using this equation, we can get C2 regularity. So we see that this is a classical solution. So to make our analysis simpler, so we start from the classical sense, but we can replace by weak sense. It's equivalent. And in this setting, we see that this condition is a necessary condition for the solvability. So people call this condition a K-sign neutral condition. So we denote it Qn, K-sign neutral condition. So let me derive this condition. It is very simple. So if x tends to infinity, this term diverge. It is a little bit formal calculation, but the derivatives disappear. And we now consider this condition. So if x tends to infinity, this one converts to end state, like this. So we can get this necessary condition. This is necessary condition. Then, before I introduce our main result, I want to introduce several notations. since we want to derive necessary and sufficient condition for the existence, so usually we need to introduce a lot of notations. So first of all, we introduce function g. This is denote the distribution of the trapped ions. So as I said that we have a lot of freedom of the trapped ions. So this quantity explains such a kind of freedom. And I said that there is another freedom. The another freedom is a maximum of the potential. So that quantity denoted by beta. So I mean that. Yes, later on we see that this G is equivalent, yes, same as this quantity. And sorry. And this quantity is exactly same as this quantity. So later on we see that. But before we solve the problem, we do not know such a kind of quantities. So we have to introduce these two quantities. Then we also introduce SegDF potential. So SegDF introduced this potential to discuss solitary wave of the Euler-Poisson equation. I just borrowed their idea. So we define this SegDF potential. And so let me explain what is this quantity. So rho sub plus minus is expected density, rho sub plus minus. So yeah, later on we see that this is really corresponding to the density of positive ions and the density of electrons. So SegDF potential is some integral of the density of electric charge. That is the meaning of the SegDF potential. So we often use this SegDF potential, but we do not need to worry about the form of expected density. So you don't need to remember this quantity. Please just remember a little bit the form of this quantity. So these are not important in this talk. And we also use these kind of anisotropic Lebesgue space. But today I did not go into the detail about the regularity of our solution. So you also don't need to read this part carefully. But to mention our statement clearly, I need to use this function space. So now, yeah, we are now positioned to study about our main theorem. So let P is greater than 2. This is for regularity, so it doesn't matter. And alpha is some number. This is the speed of the turbine wave, I mean solitary wave. And the end state satisfies this regularity. And we assume Tesla neutral condition, since it is necessary condition. And we suppose that the beta is positive, and G satisfies this regularity, and it is non-negative function. Then SW have a solution, I mean solitary wave, if and only if there exists a pair beta G. This is describe the freedom of the potential and trapped ions with these three conditions. So this is a necessary and sufficient condition for the existence of the solitary wave. The first condition is it's very simple. So if we consider alpha is equal to 0 case, so if we forget about this, so it just tells us that if end state have a end state must be even function in the C1 direction. That is the meaning of the first condition. So this one is just tell us some symmetricity of the end state. So it's not so serious condition. And the important condition is following two conditions. The first condition is segregated potential must be positive, such yes, sum between 0 to beta. And the segregated potential must be 0 at phi is equal to beta. So this is the first condition. And the third condition looks very complicated. But let me explain this one. So if we consider this integration, it must be infinite. And if we consider this integration, it must be bounded. So this condition looks very complicated, but the meaning is very simple. So this condition tells us that how much fast function b converges to 0 at phi is equal to 0 or phi is equal to beta. So let me explain more precise. If the function b is something like a quadratic function, then if we substitute this function into here, then we can get this condition. So if this quantity is diverged, we see that function b is converges to a little bit faster than linear function. I mean, much faster than linear function. That is the meaning of the first condition. And the second condition is very similar. If we consider, beta phi, this kind of the linear function, and if substitute here, we see that this is bounded. So the convergence rate at 0, convergence rate to 0 as phi tend to beta, this tells us that it is slower than linear function. That is a meaning of the third quantities. And this is a necessary and sufficient condition. And this solution satisfies this relation. This is exactly I expected. So beta corresponding to the maximum of potential phi. And f plus minus can be written by the following form. So it's really complicated. But the first line and the third line determined from the end state. Just use end state. And the middle part comes from the trapped ions. And this part explains the trapped distribution of the trapped ions. And F minus just determined by end state, like this. And I want to emphasize that this is a not complete solution formula, since we have an unknown function of phi. But this formula have a good information. If we know only phi, we can get a distribution function. So of course, if solution exists, solution must be written this form. So this is a good information to our analysis. So this is the main result. I want to mention several remarks. So our necessary and sufficient condition depending only on some physical constant and end state and the speed of the solitary wave and some functions which I introduced. It does not include in our equation. So this condition does not contain the information of the solution itself. So we can find that. So that is a good thing, since there is no information of the solution. So we can find some functions f beta g satisfies this condition, then we can get our solution. This is a good point of our necessary and sufficient condition. Indeed, we can find the example satisfies these three conditions. And it means that we can have a solitary wave with trapped ions. And we also see that it is not BGK wave. Since if solution exists, our solution must be written in this form. So sorry, a little bit complicated. And if we compare to this form and this form, you see that our solution formula is a much more complicated. So BGK, yes, model is not enough to write the solution of the solitary wave for all cases. So anyway, we can get a non-BGK wave. And sorry, I also want to say that this condition looks very complicated. Since we now consider the low regularity, but if function B have a good regularity, better regularity, C2 regularity, we can replace this integration by derivatives like this. I did not mention clearly, but if so, function B is defined by integration. So if phi is equal to 0, the function B is 0. So, and if first derivative is vanished and using Taylor's expansion, then we see that the function B is quadratic or cubic or something higher, more regular, much faster compared to the quadratic form, then we can get this condition. On the other hand, if we consider beta and we have this condition at phi is equal to beta, v is 0. And if the derivative does not vanish, it means that the function b is just like a linear function near the phi is equal to beta. So we can get this condition. So eventually, we can see that the third condition is equivalent to this simple condition. Then it's so easy to check our necessary and sufficient condition just by hand computation or using a PC. So indeed, our necessary sufficient condition is verified if the graph of B as follows. What I want to say that the function, the B must be positive, sum between 0 and beta. And at the beta, function B must be 0. And this condition tells us that the graph must be tangent to phi axis, and the graph must be across at the phi is equal to beta. So if we find some function g and f infinity and the end state, and if we draw the picture, and then we can get this graph, then all conditions are satisfied. So our condition is so easy to check. This is a strong point of our necessary and sufficient condition. Okay, I would like to briefly explain our proof. Sorry, I just talk about briefly. So let us talk about the necessity of our condition. So in this case, of course, we suppose solution exists. And then we want to show that the pair beta g, sorry, in this case, we take this number explicitly, then we want to check that this one satisfies our necessary and sufficient condition. So yeah. So now we assume phi is exist. So we can regard it given function, and we can apply characteristics method. And this is a fundamental things. F plus remains constant along the characteristics curve. And the characteristics line is given by this equation. The C is some constant. And if we change the C, we can get one characteristics curve. This picture is very similar as before. This direction is space direction, and this direction is velocity. And if we take very special number, C is equal to 0, then we can get these two bold lines. And the behavior is different. Yes, the lower area, middle area, upper area, as I mentioned. But a good thing is that now we assume the solution exists. So we can use this value. So we see that this part can be written, I mean, the F plus can be written only using these quantities. Then I omit a lot of calculations. This, you don't need to see this one. So we can get this solution formula just using characteristic method. So this part corresponding to the trapped ions. And yes, we can do exactly same thing for electrons. Electrons case is the main difference is the sign of characteristics line. For the positive ions, this part is minus, but now this is plus. So the behavior of the characteristics line is totally different. So you see that if we start from this characteristics line, it goes to this way. And if we start from this one goes to this way and go back to the end state. So there is no loops in this picture. So we can define every F by using end state. So this is the main difference between the positive ions and the electrons. So we can do the exactly same analysis, then we can get a solution formula. And here, from this analysis, we get the first necessary condition. This condition comes from this characteristics line. So on this line, F must be same. So it means that end state, this end state, and this end state must be same, owing to the characteristics line. So our first necessary condition comes from this analysis. Then we substitute this solution formula into the Poisson equation. Then we get density Vlasov plus. So we now see that this is so before I say that this is expected density, but it's really coincides to the density of our system. So still we need to change our equation. So we multiply this phi to this equation and integrate from x to infinity. We can get this equation. The advantage of this equation is the first order equation. This is the second order, but this is a first order. So treatment is a little bit easier for first order. So we use this reformulation, and this equation easily can check that if we differentiate this one with respect to x, we easily can get the product of this equation and this one. Just differentiate in x. We easily can get. this one. This is an easier way to check this calculation. And another important thing is that our system starts from hyperbolic coupled with ODE, but eventually we can get just ODE. The program can be reduced to the just ODE system and just one equation. So this equation is very nice for our analysis. So now we can get the necessary condition from this equation. So we now try to find the solitary wave which satisfies this condition. And if we substitute x is equal to 0, then this quantity is vanished at the origin. So yes, of course, phi take a maximum in here. So at phi is equal to 0, this quantity must be vanished. This is so we can get the second necessary condition. And this part is a non-negative. In particular, if x is not 0, this must be greater than 0. So we see that function b is positive. So we can get the necessary condition, second necessary condition. And let me explain the third condition. We find some x star so that phi of x star is half of the maximum. We easily can find such a kind of x star. And we consider this integral. So this we want to show that this integral is infinite. So to see it, we use change of variable. We use this relation phi, yes, change of variable, this change of variable we use. And in the middle point, the corresponding to x star, so this part is appear here, and phi converges to 0 at x tends to infinity. So 0 corresponding to the infinity in x. So we can replace our integration by this one. And now we use the second equation. So we now consider that x is positive. So the phi must be decreasing. So this part is positive. So I using this equation, we see that integrand is just 1. So we can get the infiniteness of this quantity. So we can get the necessary condition. I mean, this pair satisfies our necessary and sufficiency condition. So the next is sufficiency of the our condition, but it's so complicated. I just say that our solution must be satisfies this equation. So we start from this equation to determine the phi, and we replace this part beta and z. I mean that we first solve this equation, then we have a phi. Then after that, we already derived some solution formula by using phi for distribution function f. So if we know phi, we can determine our distribution f. And we easily can check that this phi and the f plus minus satisfies our equation. That is a proof, outline of the proof of sufficiency. So, but the proof is really complicated, so I omit it. Sorry. I also want to mention the uniqueness of our solitary wave. So you think maybe you guys expected that solitary wave is not unique since we have a lot of freedom. However, there is a rare case that solitary wave is unique. So to explain our main theorem, I need to introduce some more notations. So I introduce beta star. The definition is very complicated, but the meaning of this condition is this is a first necessary condition, the symmetricity. So this is a maximum value symmetricity satisfies. That is the meaning of the beta star. And B infinity is the segregated potential for only for non-trapped particles. I just ignore for the trapped ions from the density. So this is the segregated potential for non-trapped particles. We need to use these two quantities. The meaning is very simple, but the equation definition is very complicated. Then this is our main result for the uniqueness. So let P is greater than 2, and alpha is a number, which is the speed of the solitary wave, and if end state satisfy this regularity, and assume Kesai-neutral condition. And there exists a pair beta G satisfies necessary conditions. Here, this existence of so beta G is equivalent to the existence of the solitary wave. So this assumption is same as we assume the existence of the solitary wave. Then solitary wave is unique if and only if the first condition or second condition hold. The first condition is that there are no trapped ions, and beta is equal to beta star. And the second condition is that no trapped ions and the segregated potential for non-trapped ions must be positive, sum between beta and beta star. So this is a situation uniqueness hold. And if neither first condition nor second condition hold, there exists infinite many solutions of SW. We can have infinite many solitary waves. The proof is this is a proof, just an idea. So we find some map T, which is give the relation between beta G to our solution. And if we assume some restriction, this is a bisection map. So it's a little bit difficult to study uniqueness of the solitary wave, but every program can be reduced to the pair beta G. So to check the uniqueness, this program can be reduced the uniqueness of a pair beta G. So then, yeah, this is the outline of the proof. So finally, I would like to mention concluding remarks. So in this talk, we mainly study about the solitary wave. It has a global maximum point. And we find necessary and sufficient condition for the existence. And we also clarify in all possible cases whether or not it is unique. So this is our main result. Of course, there are other traveling waves. So we also did analysis of shock wave and wave trains. So let me define the shock wave. It comes from the analogy of fluid dynamics. We call solitary wave. That traveling wave have this kind of shape. This is for phi. Phi converts to some constant at the far field, and it is monotonically decreasing. In this case, we call shock wave, and the wave train is phi has some periodic pattern in X, and it travels in this direction. So this is a wave train. Maybe this terminology is a very standard. Then I would like to summarize our result in this table. So for solitary wave, as I said that we can find necessary and sufficient condition. And there is a case that it is unique. Other case, always we have infinitely many solitary waves. For the shock wave, we also can get necessary and sufficient condition for the existence. But the shock wave always unique. Since if we look at the shape of the phi, like this, there is no potential barrier, so we do not have any trapped ions. So we can show the uniqueness. For the wave trains, of course, we can get the necessary and sufficient condition. But for the uniqueness, we always have infinite many solutions. Since it has a periodic pattern, so for the wave trains, we cannot put even end state. So we have a much more freedom for the wave patterns. So we easily can get infinite many solutions. I want to stop my talk here. Thank you so much for your kind attention.
Thank you very much, Masahiro. So very good, very nice talk and very deep result. So maybe the audience now have some questions. Just unmute your microphone and ask.
Hi, Masahiro Sensei. Can I have a question?
Yeah, of course.
Yeah, a nice talk. Thank you so much. Nice to meet you again. And I'm Jin Long Chen, and I have some questions about the. Can we have about the energy momentum for your solitone wave?
Energy momentum.
Energy momentum depend on the, for example, depend on the velocity of something.
Oh, sorry, I did not know the energy momentum. I mean,
usually you prove the existence and the uniqueness for the solitone wave. And can we have any? Can we come back to the equation? Can we, for such equation, for such solution, can we have some energy momentum something or energy estimate or for this solitone wave?
Sorry. 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 I just don't know the terminology of energy momentum. Energy momentum means
energy momentum.
I see. Sorry, I did not consider such a kind of things. Maybe you asking some energy conservation law or something like that. Energy identical or something like that. Is it right?
Okay, thank you so much. And the second question is do you have any nonlinear stability for your solitone wave?
It's a very interesting question, and I really want to consider it, but I did not get any result yet. Since, yeah, to be honest with you, I do not know how affect these trapped ions to the stability analysis. It's so interesting question for me.
Thank you. But your numerical simulation seems to tell us it's stable.
This is just a traveling solution itself, so it looks like stable. But I don't know. So if we put some small perturbation here, I don't know potential barrier how behave. I should do some numerical. Yeah, we should start from the numerical simulation. Yes, thank you for your good suggestion.
Thank you so much. Nice talk.
Thank you so much.
Nice talk. Thank you so much.
And so, Masahiro, I have a question here in this very nice picture. So I am trying to understand your technique. and I think somehow you are kind of using the shooting method. And the blue line, this F plus is some kind of like amplitude of your limiting profile or something like that. And this phi is also some shooting parameter. Is that true? Or can I interpret in this way? Because you want to find Hoboken orbit of your PD, right? Like solitary wave is like a solution connecting to equilibrium. And I think in the limiting profile, or at 0, you are shooting. You are shooting to the infinite, and then you use these two parameters for shoot.
Yes, you're right. That is the idea to show the, for example, infinite many solutions. I mean, firstly, we find one solitary wave, and we exactly I did you explained. We shooting G and beta. We choose we slightly making difference, and so that it satisfies the necessary and associated condition.
Yes, but how about the unique solution? Do you also use shooting or?
Yeah, we show that. Yeah, for the uniqueness case, we just show that we have only one pair. So we, in other words, we show that we cannot use a shooting method. I mean, even if we any shooting, we cannot find other pair beta G.
Okay, thank you. Yes. So other question, comments, remarks?
I have a question.
Hi, Jinsei, welcome.
I'm sorry, I'm late. Yeah. So for profile for phi electric field, it's obviously it looks like a solitary wave and shock wave and wave trains.
Yes.
But for instance, how about the profile of F? For instance, let's focus on the solitary wave case. P is a solitary wave, symmetric about the origin. Then how about the shape of the F?
Yeah.
F4 ions and F4 electrons.
Yes. It is a good question. Yes. I did not check but this form can be written by using this formula. So we know already why if we find the solitary wave. And if substitute it into here, we can get F plus. But it's so complicated for me. And maybe it is better we just look at the density, the integration of F plus.
Oh, then is it solitary wave? Integration of F is
yes,
solitary.
Yes. It also have this kind of shape.
Okay. Okay, I see. But because I was wondering, what is the shape of some solitary waves or shock waves in the microscopic description? That was my question. But it's just very complicated. So.
But for wave trains, so easy to see, since it has a periodic pattern for phi. So F plus must be have a periodic pattern. Only X appear in this with phi. So it's easy to see that if phi has a periodic pattern, it also have a periodic pattern.
Okay, I see. Thank you.
And so I have another question. So, but this may be fact, but for Professor Chen asked you about the stability, and what do you expect? Like, for example, maybe one may expect that unique solution should be stable, but infinite many solutions are not stable, or something like that. Like, what's your expectation about the spatial stability?
Yes, yes. You say time asymptotic stability. So, or sorry, so I could not catch
Yes,
that.
the usual. I mean, for example, if you consider linearized problem, which case do you expect that there's a eigenvalue with positive real part or positive spectrum?
I think that
in real part?
every case, the eigenvalue is located in the real axis. I mean, imagine. Yeah. So sorry. So I mean that the imaginary part is always zero, I think. Since this is a Vlasov Poisson equation, usually it does not have a dissipative structure. Of course, if we put a very special Xi, we can find some random damping. But this is when we find the solitary wave, maybe random damping does not affect a lot. Otherwise, we cannot catch a solitary wave. So maybe we do not have any dispersive effect. So yeah, I think that is the main difficulty why I could not consider stability yet. And my conjecture is that if, of course, just let us talk about stability, linear stability, not nonlinear one.
Or spectral stability if you want.
Yeah. So maybe the one possibility is using some weight function. It is, yes, for the Vlasov-Poisson equation case. So Junshi did some linear stability analysis by using weight function. So maybe that is one possibility. We also use some weight function, and we consider the case that the key point is that all particles going to the same direction. Otherwise, the weight function does not work well. That is my understanding. So one possibility that if we take, for example, 0, Xi1 is yes, positive, and we put some number, I don't know, some number, some function, x plus minus, yes. Xi1 is 0. So I talk about alpha is equal to 0 case. Then if we put some very special end state, there is no particle in this area, and the particles just appear in here, and there is no trapped ions. So in this case, there is a possibility we can get linear stability. That is my understanding. But the other case, it's so difficult. I don't know.
Okay, I see. Cool. So other question, comments, remark? Yes, I just found a question for the Taiwanese audience. Because in Taiwan, some people, they are interested in the dependence of the OSB on some parameters. For example, if I fix all parameters but just beta, say, they want to prove whether alpha prime of beta is positive or negative, monotonicity of the OSB. Do you expect that such monotonicity of the OSB on some parameters exist?
So at least, my result, first we give beta, then we checking this condition. So I don't know the property of alpha so much. We just put any number, then we find the end state so that it satisfies these conditions. So yeah, I don't know.
But what happens if I change the end state? Then should alpha be bigger or smaller?
It's a good question. It's
because in your case that's interesting because your travel exists for all alpha and and it's given because for in many cases the wave speed is unknown. But in your case, wave speed is given, and that's
Yes,
interesting.
yes.
Yeah.
Sorry. Yeah.
People
Yeah.
usually derive an integral relation of the wave speed to the solution, and then they take derivative or they try to insert some test functions to estimate the derivative of alpha.
Yes.
Yeah.
Yes. Yes.
But in your case, alpha is given, so that's why it's this kind of question is weird for you. But if you change the end state, maybe you can try to see what happened. Like inverse problem, I don't know.
Yeah. You're right. But yes, main quantity to define to define our necessary and sufficient condition is this Vlasov segregated potential. And if we look at the potential, okay.
So Masahiro, I have a more fundamental question.
Okay.
Right? Is the sign of the wave speed important in your Vlasov Poisson setting? Like positive or negative, it's not important.
No, not so.
Okay. Then I think my question is not a question anymore because for the population dynamic, there are two species like a wolf and tiger, this and that. If wave speed is positive, then one species wins, the other dies. So that's why the wave speed is important for the population dynamic.
I see.
But if maybe in your case this is not important, then yes.
Yes.
I see.
So if we consider the solitary wave of the Euler-Poisson equation or some other dispersive equations, so we can take any number of the traveling wave at the speed of alpha. Not traveling wave, solitary wave. But you see that if we consider shock wave, if we consider the, for example, fluid equation, alpha give us alpha must be defined by the end state. If we define some end state, alpha is automatically determined. So for shock wave, we have a similar situation. So alpha must be satisfied some relation. The relation is written by the end state. So that part is very different from the solitary wave and the shock wave. Shock wave case, we have a lot of restriction for alpha. That is true.
I see.
I have a question. So, does your result include the steady state solution case where the alpha is 0?
Yes,
So
I
here
think so.
Yes.
Yes. Cool. Very good. So, other question, comments, remark? Okay. If it is not the case, let me finish this with asking the next question. Because in Taiwan, I think this solitary wave for Vlasov Poisson, maybe Professor Chen is expert. But if I study radiation diffusion equation, this kind of result is removed. So, in your opinion, what is the most delicate part in your analysis? What is really only the expert can know? Outsider cannot know. Can you indicate some idea to us?
Okay. I don't know.
This is for students and for me. Okay. So for you, all analysis is natural.
Natural.
For standard.
For standard. So of course there is some hyperbolic equation. So we use characteristics method, and we write down our solution. Then we substitute the Poisson equation to get the simpler equation. That is a main key idea of our proof. I mean, so to get this equation is a key idea. So
I think so. Yes.
Then after that, it's very, yes, in some sense, it's very standard. Other people can do the more detailed analysis of this equation.
Yeah. And how about the choice of this beta? No, not beta. These two parameters, f plus 0 and the square root of phi naught. Is this idea new or standard?
Maybe new. I do not see any papers since at least for the mathematician, just consider BGK wave. If we using BGK wave, we do not need to worry about the trapped ion too much.
Mm-hmm.
So this is a new idea, I think. Yeah. Thank you for this.
Amazing, really. For me, I think your idea is very natural to me as an ODE guy, okay, as a dimension guy, because I use shooting method a lot. This is just a shooting parameter, but I understand this is very smart. Yeah. Okay, cool. Okay, so maybe let's thank our speaker, Professor Masahiro Suzuki again. Yeah, thank you for giving this very nice talk. Good. Yeah. And so you also have a result on so if the audience want to discuss further or chat, then you can you are very welcome to stay. Yes. Good. Oh, thank you.
Yeah, thank you.
Thank you
And
very
you
much.
have much more result even for the shock wave and the periodic chain. So in your paper, you prove the existence of a solitary wave and shock wave and periodic wave chain.
Yes, everything.
Wow, everything amazing.
Yeah, but
And the technique is similar or there's essential difference?
Essentially, yeah, technique is the same. Yes.
Okay.